Welcome to the class of electric drive and controller. We are going to see about the drives and the controllers required for a pure electric vehicle and a hybrid electric vehicle. We all know that the electric propulsion systems are the heart of pure electric vehicles and hybrid electric vehicles. The propulsion systems are the systems which are required to propel the vehicle. The electric vehicle consists of electric motor, power converter and electronic converter. The electric motor in an electric vehicle converts the electric energy into mechanical energy to propel or move the vehicle, or it acts as a generator converting the mechanical energy available at the wheels to electric energy during braking, and that electric energy can be used to charge the battery. The power converter in an electric vehicle supplies proper voltage and current to the electric motor. The electronic controller gives the commands to the power converter in the form of control signals. It also controls the operation of the electric motor to produce the required torque and speed as per the commands from the driver. The electronic controller consists of three functional units: a sensor, interfacing circuit and a processor. The sensor is used to transform the measurable quantities, say current, a voltage, temperature, speed, torque or flux into electric signals. These signals are conditioned by the signal conditioning unit to the appropriate level before being fed into the processor. The output signal of the processor will be amplified through the interfacing circuit to drive the power semiconductor devices available in the power converter. This is the functional block diagram of a typical electric propulsion system. So we have electronic controller, power converter, electric motor, a storage device which is connected to a power converter. The choice of the electric propulsion system depends on the driver's expectations, vehicle constraints and energy source. The driver's expectation is defined by driving profile, which includes acceleration, maximum speed, climbing capability, braking and range. The vehicle constraints includes volume and weight of the vehicle. The energy sources relates to batteries, fuel cells, ultracapacitors, ultra flywheels and other hybrid energy sources. This process of selecting the features has to be carried out at the system level. Motors in electric vehicles and hybrid electric vehicles usually require frequent start and stops, high rates of acceleration or deceleration, high torque, low speed hill climbing, low torque and high speed cruising and a wide speed range of operation. Coming to electric drives, we have commutator motors and commutatorless motors. Conventional DC motors are commutator motors. They need commutator and brushes to feed current into armature. So it is less reliable and not suitable for maintenance-free operation and high speed. As winding excited DC motors have low specific power density, and DC motors are mainly used in electric propulsion systems because of their mature technology and simple control. Seeing commutatorless motors, the advantages are they have higher efficiency, higher power density, lower operating cost, more reliable, and maintenance free operation. Induction motors are widely used commutatorless motors. They are widely used because of low cost, high reliability, maintenance free operation, but we don't get desired performance using conventional control methods of induction motor. As power electronics has emerged, the principle of field oriented control or vector control of induction motors are used to overcome their control complexity. Field oriented control used motors, they have some problems like low efficiency at light loads and limited constant power operating range. Seeing conventional synchronous motors, these conventional synchronous motors can be replaced by permanent magnet motors. The field winding of conventional synchronous motors are replaced by permanent magnets. Permanent magnet synchronous motor can eliminate conventional brushes, slip rings, and field copper loss. The permanent magnet synchronous motor or brushless AC motors. They can run with sinusoidal or pulse width modulation supply without electronic commutation. Permanent magnet synchronous motors use field oriented control to get high performance, and they are used in high performance applications. They have high power density and high efficiency. One more type of commutatorless motors are brushless DC motors. The DC in brushless DC motor, it doesn't denote the direct current. This motor is fed by rectangular AC current, and it is also called as rectangular fed permanent magnet brushless motor. The major advantage of brushless DC motor is the ability to produce large torque because of rectangular interaction between the current and the flux. The brushless configuration allows more cross-sectional area for armature winding. It also has high power density as electric loading is increased, and permanent magnet BLDC motors operate with shaft position sensors. Sensorless control technology has also been developed by Texas. Next we have switch reluctance motor, which has simple construction, low manufacturing cost, and outstanding torque speed characteristics. So due to this torque speed characteristics, they are used in electric vehicle applications. This SRMs operate with shaft sensors to detect the relative position of the rotor to the stator. The presence of this position sensor reduces the reliability of SRMs and constrains some applications. In switch reluctance motor 2, we have sensorless control technology. And seeing the induction motor, we have two types, wound rotor and squirrel cage rotors. Synchronous motors, we have wound rotor, permanent magnet rotor and reluctant synchronous motors. Based on the applications, let us see the performance of the DC motors in the next video. Thank you.